Good morning, class. Let us begin today with some inspiring words from St. Augustine. Breathe in me, O Holy Spirit, that my thoughts may all be holy. Act in me, O Holy Spirit, that my work too may be holy. So today's lesson is on the ideal gas law. So let's recap by considering three of the laws that we've looked at describing gas behaviors so far. We saw that with Boyle's law, pressure and volume were inversely related, and so that meant P times V would be a constant. Let's call that A. In Charles' law, we saw that volume and temperature were directly related, and that led to V over T equaling a constant. Let's call that B. A reminder, temperature must be in Kelvin for that to be true. And then we finally saw that Avogadro's law told us that volume and moles of gas were also a direct relation. So V over N, where N equals moles, equals another constant. Let's call that C. So these relations show together how volume of a gas depends on pressure, temperature, and the number of moles of gas that are actually present. So now if we would combine all of those equations, notice that we would end up with P times V over N times T equals a constant. So we're going to put all those constants together and now call them K. That, again, is only true if temperature is in Kelvin. So if we just do a little bit of algebraic rearrangement, we see that pressure times volume would equal N times K times T. So now all that we are going to do is give a special name to that constant, and that means we're going to use a new letter to represent that constant. And what results is what is known as the ideal gas law. PV equals nRT, where R is the ideal gas law constant. So the ideal gas law is extremely useful to chemists because notice this is the first equation where we are going to have a quantity in it that represents all of the different conditions of a gas at one set of conditions, rather than looking at how things are changing. So PV equals nRT. Now, if R is a constant, why aren't we simply putting a number in there? Well, let's think about that for a moment. We know that T is a unit, or temperature, and its unit must always be Kelvin. N must always be moles. But what about P and V? Think of all the different units you know for pressure: atmospheres, kPAs, millimeters of mercury, torr, etc. Volume, we could have feet cubed, inches cubed, decimeters cubed, liters. The list goes on and on. So R is definitely dependent upon the choices that we would pick for pressure and volume. R would be a different value for every different pressure and volume combination. So that's going to get a little difficult, too many R's to know. So what chemists have chosen is a few basic R's, and your textbook likes the value of R equals 0.0821 liter atmosphere Kelvin moles. So what that means is as long as we have pressure in atmospheres, volume in liters or decimeters cubed, temperature always has to be Kelvin, we don't have a choice there, and N always needs to be moles, R will indeed always equal one number, and that number will be 0.0821. So as we look at problems, if they would give us a pressure in kPa, we would only be able to use the 0.0821 if we change the kPa to atmospheres. If they gave us a volume in milliliters, we would have to change it to liters before we could use it in the equation along with the value of 0.0821 for our R. So what are our clues going to be that the ideal gas law will apply? First of all, the biggest thing is that we are only talking about one set of conditions with this one gas. So there's going to be no mention of a new volume or a new pressure or a new temperature or a change in moles. So let's look at an example problem. 32 grams of oxygen gas occupy 24.69 liters at 100 kPa. We want to know what's the temperature of the gas in degrees C. So what's our clue that we want to use the ideal gas law? We see that we have one gas and one set of conditions. There's no talk about the volume changing, the pressure changing, any gas amounts changing, and they just want to know what is the temperature at this set of conditions. So we know that we are going to use our equation, PV equals nRT. So a good place to start, what I suggest, is that you always fill in the R value first. And a reminder, we are going to use the one that your book prefers, 0.0821 liter atmosphere over Kelvin mole. Funky units. Right? So now we're going to go and look in our equation, and we are being asked to find temperature. So temperature is our unknown, and we simply need to plug in all the other values. But if we put that R in first, we are going to be reminded as to which units every one of the other variables must be in. So pressure, because of my R value, pressure must be in atmospheres. So we come over to the problem and we see that they gave us the pressure in kPa. So we're going to have to do a conversion there. So we have 100.0 kPa, and we want atmospheres. That's an easy one. 1 atmosphere over 101.3 kPa. And 4 sig digs in this case because of the way the 100.0 kPa was given to us. 0.9872 atmospheres. So we'll plug that up in our equation for P. Next, we need something for volume. We look at our R value. We see that it has to be in liters. Luckily here, we don't have a conversion to make. So we're simply going to plug the volume in as given. So times 24.69 liters. And now we need N. A reminder that N is the number of moles. So we come over to our problem, and yes, we have more work. We were not given our answer or our information in moles, but in mass. A reminder, oxygen is diatomic, so that's O2, so 32 grams times 1 mole of O2. Looking at our periodic table, we see that that would be 32 grams, 2 times 16. So nice, easy math. We have 1 mole of oxygen gas present. So this is times our R, and I'm going to put a 1 in there with the mole, and we should really have that as 1.00 if we're going to keep our significant digits. All right. Now, some reminders on trying to get our units correct. If things are on opposite sides in algebra, they would cancel. So our atmospheres are going to cancel. We can see also that our volume unit would cancel. And because moles are units on the same size, this one's in the numerator, that in the denominator, that will also cancel. So no surprise that when we find this and do the math, the final answer will be in Kelvin for temperature. All right, so now we just need to get out a calculator and plug away here, and we get 24.36903 equals 0.0821 times T over K for our unit. A little more rearranging. Plugging that in the calculator, we get temperature equals 297 Kelvin. Now notice we haven't answered the question because they wanted the temperature in degrees Celsius. So we'll have to subtract 273 from that, and our final answer would be T equals 24.0 degrees C. 3 significant digits, because if we look at our original data, we see that all of the information were given was either in 3 or 4 significant digits, so we go with the 3. Let's look at another example. We see that we have one gas, helium, at one set of conditions. So we know that the ideal gas law, PV equals nRT, applies. So I want you to pause the video, work on your own, and then come back. A reminder to start with your R value to help you get through all of the other variables with the proper units. All right, so if we make all the necessary conversions, and I'm trying to color coordinate it for you here, we had to change our volume to liters to go with our R value, our N to moles, calculation up here, and our temperature to Kelvin shown up here in the box. Now it's just simply putting everything into the calculator and doing some of our simple algebra. Again, putting that all in the calculator, I get 3.01. I look at the original problem. Every one of those numbers given to me had 3 significant digits, so I'm going to round the final answer to 3 significant digits, and I have 3.01 atmospheres. So you should be set now for tomorrow as we tune in together for a live class session where we'll do some more practice on applying the ideal gas law.